Welcome back, viewers and subscribers. Part 2 of the series on parallel circuit being destroyed. Alright, so we are destroying this series on parallel circuit. Now, in the last video we were calculating, we found out that this RT here, the total resistance, would have been equal to 4 ohms. Alright, let me just put that in. So it would have been equal to 4 ohms, right? Now today, we'll be finding the total current and the individual currents going around the circuit, and this is going to be exciting right here on Green's Electrical School. Okay, so IT, we were finding the total, which means current total. So we're going to find what IT is right away. Now naturally, according to Ohm's law, if you found the total voltage and you have the total resistance, then we can confidently calculate the total current, and we're going to do that right here and right now. So here we go. IT would have been equal to VT, which is the total voltage, over RT, the total resistance, which will be equal to 12 volts, right, over 4 ohms, right? And our answer would be 3 amps. So therefore we would find IT right here. We can plug it into our circuit. We know, so now we know that 3 amps is flowing around the circuit from the source. We have a maximum of 3 amps flowing around the circuit, and so that means what happened here, some of this 3 amps going to share right here to this resistor, as we explained in a previous video. It's going to share right here, and some going to go all the way out here, come around to this series group, come down to this parallel group, and all that madness. So we're going to find out just how much is going out here, how much is right here, how much go to this resistor, how much go to this resistor, how much is this independent resistor taken from the circuit. And we're going to find out that right here in a short while. Okay guys, so let's find the individual currents. Here we go. So right away, this resistor is R1, so therefore we need to find I1. Now what do we know about this resistor? It is independently connected, right? It has its own independent connection. It's parallel to everything, and so normally the voltage that's reaching this resistor is the full voltage. Would have been the total voltage of the circuit. It's reaching this resistor full time, because remember, in a parallel circuit the voltage is constant. So this resistor will be receiving the full 12 volts right here. So we know the resistance that it has, so we can confidently calculate how much current it is drawing from the circuit. And we're going to call that current right here, we're going to call it I1. Alright? Which means the current flowing through the first resistor. And that would have been equal to, either call it the total voltage, because the total voltage is going through it fully. So VT over R1 equal to 12 volts, right, over 8 ohms, right? And that would have given you an answer of 1.5 amps. Right, so right away we know that 1.5 amps is flowing to this resistor here, and we can plug it in. We can write it in so we have a better understanding of what is going on. So I1 equal to 1.5 amps. And already this circuit is starting to make sense, viewers and subscribers. So what we want to know is the rest of the current that is, so we know that 1.5 amp is shared down here. We want to know how much of it is going out here now. Now, a simple way to do this, we can minus this 1.5 amp from the total current, because we know that 3 amps is flowing in the circuit, and if this resistor takes out 1.5 amp, then it means that the rest of it will be going towards this direction. Remember, now it is parallel circuit, so the current gonna split, right? So if you minus 1.5 amp from 3 amps, you would have 1.5 amps going out here as well, right? So we know that 1.5 amp is along this line right here, right? So what do we see? We see a series circuit, and remember, the laws of series circuit is that once resistors or a load are connected in series, then the current is constant, meaning the current that's reaching the resistors doesn't change. So what that is telling me that this resistor and this resistor right here would have a current of 1.5 amps. So we can easily plug that in without even calculating it, because we know the laws of Ohm's law and the laws of a series circuit. So we can easily plug that in and say this. We can say, just a minute, I2 would have been equal to 1.5 amps. Yes, it will. And I3 would have been equal also to 1.5 amps. So I2 and I3 represent the current flowing through R2, and we can plug that in, and we can say this is I2 right here. I2 would have been equal to 1.5 amps, and I3 equal to 1.5 amps. Right, so that we'd have got that answer right there, viewers and subscribers. So what we want to find out now, remember, this gets a little tricky here now. So we have the current. We know that the current flowing through these guys is constant, 1.5 amp. But when the current reaches this point right here, it's going to split. So I'm going to go over to this side because this is the parallel connection. Right? So I'm going to go over to this side, and so I'm going to go over to here. So the question is, there's a simple way to find this out, being as we have two equal resistance, but I am not going to do it that way. I want to show you guys how you would arrive at your answer. Right? I want you guys to get knowledge of how this thing really works. So we're going to find out what happens to the current. This 1.5 amp here, something's going to happen to it right here, but we're going to have to take a different route to find out what happened, because it has to split. Just like how this 3 amps here, this is the source, and it split when it reaches this parallel section. This is the same thing that's going to happen to this 1.5 amp when it reaches right here. It's going to split, and some going to get some, and this resistor going to get some of it. You understand? But in the end, it still have to work out back to the 1.5 amps, and everything going to balance out back to 3 amps, back to the source. But what we're talking about is this right here. We're going to find out what is happening. All right? Okay, guys. So remember now we're investigating what happens to the current when it reaches this direction right here. So remember now, viewers and subscribers, we have to understand how these kind of circuit work. So remember, we find the current here. We know the current here, 1.5 amp. We know it right here, and we have the resistance. So we cannot say what this current is because we don't have two values. We only have the resistance right here. So we have to find out, in order to find any value of anything when it comes to a working circuit, you have to have at least two values, right? But in this parallel group, we only know the resistance. That's the only thing we know. We don't know the current, and we don't know what voltage is reaching them, right? So we have to find the voltage. But first, we have to find out, remember now, in a series circuit, the voltage here in this resistor is 12 volts. Remember that, because it is connected in parallel with the source. So you'd have received the full 12 volts. But we don't know the voltage going through the series circuit. Remember, in a series circuit, the voltage varies. So these two resistors, 1 and 2, would have given a voltage drop. You'd have 12 volts coming in this line, but they would give a voltage drop. And we're going to find out what that voltage drop is. So we have to calculate that right now. Alright? So I'm going to say a voltage drop. Alright. Sorry, I spelled volt wrong. Sorry about that, viewers. Voltage. Yes. A voltage drop, right? Okay. So we're going to calculate that voltage drop right there. So for I2, we're going to call I2 the voltage going to the second resistance. So we're going to call it V2. So we have the amperage and we have the resistance. So we can easily calculate the voltage drop that it gives. So here we go. We're going to say V2 equal to 1.5 amps. And we know this by Ohm's law. To find the voltage, you multiply the current by the resistance. So 1.5 amps right here. I'll give my 5. That's a 5 right there. 5 amps multiplied by the resistance, which is 4 ohms, right? We got that right there. Our answer would be equal to 1.5 multiplied by 4, and our answer would be equal to 6 volts, right? So our V2 would be equal to 6 volt, and we can plug that in. So it gives a voltage drop of 6 volt. This resistor here, so 6V. We'll put that in there, right? And we know we're gonna go to V3. This resistor, we're gonna find the voltage right here now. All right, that the voltage up that this resistor gives. So here we go, V3 equal to, we know the amperage, which is 1.5 amp because they're both in series, multiplied by the resistance is 3, yes, resistance is 3 ohms, and our answer would be equal to 4.5 volts. So that would have been the voltage in this second resistor, the voltage drop that it gives. So we can put the 4.5 there. Let's put the 4.5 volt there. Alright, yes. So we know that they give a voltage drop each. So what we're going to do to find the total voltage drop that they give, we're going to have to add the two voltage values, and then we can know the voltage drop that both of these resistors give. So we're going to add V3, or V2 I should say, V2 plus V3. See, we have to take a lot of roads for this circuit, and that's excellent. It gives your brain a chance to stretch, which is good. Equal to 6 volt plus 4.5 volt, and that would have given you an answer 10.5 volts. So that is the voltage drop that we will get from these series resistors. So what we're going to do, we're going to subtract this value from the main voltage, right? And that would have given us the voltage that's going to be at this point right here, that is entering into the parallel section. And once we know the voltage, then we can calculate the individual currents that each resistor contains, right? Because remember, in a parallel circuit, the voltage doesn't change. So if you, whatever voltage we get at this point is going to be the same voltage right across these two. So which means V4 and V5 would have been equal to the same thing, right? So we're going to get to that right away. So the total voltage drop is this. Total voltage drop would be, we're gonna say 12 volts. Yeah, the main voltage here, which is 12 volts, minus 10.5 volts, all right, which have been equal to 1.5 volts. So that is the voltage drop, after the voltage, because you would have had the 12 volts coming here. You'd have had the 12 volts. This is the DC source, 12 volts. You'd have it coming here, right here. Sorry. You'd have had the 12 volts coming right there, but as it goes through this resistor, it's going to be a voltage drop, right? You're going to take away, this resistor going to take away 6 volt, and this resistor right here going to take away 4.5 volts. Going to leave you a remainder of 1.5 volts, which is right here, right? Because of voltage drop, because they are connected in series. Remember, in a series circuit, the voltage changes. So therefore, it's going to affect, once you have an incoming supply to a series circuit, it's going to affect the output that these resistors give, right? They're going to take away something from the voltage, and they're going to leave you with 1.5 volt. So what that means, I have 1.5 volts coming to these two resistors due to the fact that they are connected in parallel. They will not give you a voltage drop because they are connected in parallel. Remember, in a parallel circuit, the voltage doesn't change. What changes is the current, and that is what we are digging to find. Okay, so we're going to find the individual currents of R4 and R5, which would have been I4. We're trying to find I4, and we're trying to find I5. Okay, these are the unknowns, and we're going to find them out right here at Green's Electrical School. this circuit is very excellent. I enjoy working through this. So I4, here we go. We're getting ready to find this individual current here. I4 would have been equal to, remember we know the voltage here, so it would have been equal to, according to Ohm's law, to find the current, you divide the voltage by the resistance. So we know that we're going to use this voltage here for I4, 1.5 volts, yes, over 2 ohms, right, which would have given us an answer of 0.75 amps. So that would have been I4. We're going to put it in. I want to pretty up the circuit. That's the amperage going through that resistor right here. Now we're going to calculate I5 now, viewers and subscribers. I'm sure you're enjoying this circuit as much as I am enjoying it. It is very excellent, and it's very straightforward. Once you learn the technique, folks, you can do any circuit. Trust me, you can do any circuit. 1.5 volts over, again, the same, they have the same value, 2 ohms, right? 2 ohms, which will be equal to the same 0.75 amp. Now remember, we use the same voltage because 1.5 volts is coming here, and these are connected in parallel, so it's gonna have the same voltage. So which means V4 would be equal to 1.5. Let me just write that down. So V4 equal to 1.5 volts, and V5 would have been equal to 1.5 volt. They're the same thing because they're connected in parallel. So that's what would have worked, folks. And all of it will work together. All the voltage would add up back together and give you back the same 12 volts, right? And all the currents would add up together and give you back the same 3 amps. But we're just showing you how each load is distributed around the circuit. And I'm sure you guys enjoyed this. And it is my pleasure to show you guys how this stuff works. At first it looks a bit confusing, and you can say, all right, sometimes you get confused when you see these things. But once you know the know-how, then you can attack any circuit in the world, and you can tear that down and destroy it, because that's what this video is all about today: destroying circuits, destroying them. So please remember, you have to take it whenever you're doing circuits like this design here, where this is an individual connection, different from the rest of the circuit. It's an individual parallel connection. Then you have to calculate it. Once you find the total resistance on this side, you have to calculate them in parallel. You cannot convert it to a series circuit. Please remember that, viewers and subscribers, because you will run into problems. I'm telling you, you will run into problems. You see, you cannot calculate it like this one, as I showed you guys earlier. You cannot calculate it like this one. This have a series connection first, and then you have the parallel connection. Now, once you would have worked out the parallel connection, you can calculate the total resistance in series. You draw the circuit like this and calculate it in series. What is not so in this case, because you have an individual parallel connection, and it is connected in parallel to the rest of the circuit. So once you find the total resistance here, you calculate them in parallel. You understand me? This would convert to one resistor, you calculate it in parallel to this, right, to arrive at your answer. Otherwise, you are going to run into problems. Please remember that. All right, I'm your guys, Mr. Green. So thanks for making it Green Electrical School. I do hope to see you guys again next video. Hope this video helps. Please like, share, and subscribe, and tell your friends about it. And I can tell you there's more exciting videos to come from right here. And we do hope you stay safe. All my U students watching this from UTech, and all the university students from across the world, high school students, I thank you for watching this video, and do hope it's helped.